happy to have Nat Levine visit us today and tell us about convexity of scaling dimensions over conformal manifolds.
Thank you very much. Thank you very much for your hospitality. Very nice to spend a couple of days here in NYU, and I look forward to discussing with many of you. So this project is about convexity of scaling dimensions in CFTs with conformal manifolds. It's a work in progress, so you should feel free to interrupt with questions, and your feedback is most welcome. So let me give you a scenario. I can minimize this first. Okay. So I'll give you a scenario. I don't know how much this happens on this side of the pond, but sometimes you're in a talk, and it's an integrability talk, and someone shows you this plot, or a similar plot. These are single trace operators at n equals infinity, planar theory, in 4D n equals 4 superangles. Okay, so they compute this using integrability. There's this technology called the quantum spectral curve. I guess you're all kind of vaguely familiar with this picture. And you're looking at this, and then you kind of say to yourself, oh, they're all monotonic. And you ask the speaker, why are they all monotonic? And it says, well, why not? The integral theory, simplest possible thing. They have to blow up at large lambda. This is the top coupling, lambda. So, why shouldn't they be monotonic? Okay, and then you think, okay, it feels a bit fishy. And then you plot them as a function of lambda instead of square root lambda. Well, these guys did in their paper. It's the same curves. And you see that they're actually concave functions. And you realize for functions which blow up at large lambda, concave implies monotonic. Because the first derivative is positive at the end, and they're curving this way. And you think, okay, maybe concave is something I could prove, right? Because, well, as I'll explain later, concave is something you can, under some assumptions, prove. But this was infinite n, and it's going to be much easier for us to start with finite n, for reasons I'll explain later. Infinite n will be a sort of somewhat singular limit of my work. So let's see how the picture changes at finite n. This infinite n picture, as was kind of schematically drawn by these people, the level crossing associated with integrability in the planar theory gets resolved in a way a bit like this. So in this theory, it can't be true that all of the curves are concave anymore. Because you see, like, well,
the orange lines are protected operators.
Orange lines are like some protected double traces, yeah. So you see, like, all but the lowest one are kind of bouncing around up and down. The level crossings get resolved, and they have to kind of curve quite sharply in both directions. So they can't be concave. But the lowest state still looks concave. And this lowest state is going to be the domain of validity of my work. So I'm talking about the lowest state. And now you convince yourself there maybe really is something you can prove here, because if you look at finite n, right, that was all infinite n, but let's go to finite n. So the only data I really know of is from these authors, and these are bootstrap upper bounds, but they kind of claim that the upper bounds are basically saturated by n equals 4 theory, because they use this data from localization, integrated correlators. And so you see that you should only, these walls are supposed to show you you should only look left-hand side of each wall, because the other side is just related by S duality. So we just look on one fundamental domain, and on this fundamental domain, indeed, these curves for different values of number of colors, they're all concave functions of lambda. If you take these upper bounds as kind of saturated, then they look concave. It seems like, pretty compelling concave picture. I would maybe show you this at the end, but I'll just show you now. This is an example from 3D. Qualitatively, if you look in one little cell, which is a fundamental domain, looking away from cusp points, this lowest operator in that theory also looks concave. It doesn't have any minima in the middle. So that's just qualitative. So that's the end of the slides.
Okay. Just to be sure, so
yeah.
Concave. I mean, of course, when you track the lowest dimensional operator, there could be points where there are other branches. So you're talking about locally concave.
Yeah, it's local, and I guess I need to, as I'll say in a minute, I need to assume a certain amount of some kind of analyticity.
Yeah.
Splitting maybe is. Maybe if you have some level crossing, you can analytically continue through. But normally you assume no level crossing, I guess, in most theories.
Yeah.
Some splitting, yeah. I can't really probably handle the splitting point.
Right, you know very well in like the two-dimensional example, like the lowest operator, if you're close to the boundary of conformal manifold, there's no level crossing. But interior, you can't do level crossing.
Sure. Well, I also have some assumptions which may rule out certain 2D examples.
Uh-huh.
So let me close the slides. I don't really know how, but okay, thanks. Do that now. Can I just go ahead?
Yeah.
So let me just go ahead and state the results. So my assumptions are going to be that I'm dealing with a unitary CFT in any dimension. You can see over here. Yeah. And I assume that it has some exactly marginal operators. Right. So we want a conformal manifold like this n=4 example we just discussed. In that case, the Yang-Mills coupling is the marginal coupling. So we're going to have some conformal manifold. And I'm going to make one more assumption, which is going to do a bit of heavy lifting for us. So I assume that the finite part of the sphere partition function, Z, is unambiguous. I'll just take a moment to explain what that means. So in general, the partition function of the CFT on the sphere is a divergent quantity. But in odd dimensions, it just has power divergence. Stop sharing. Okay.
Thank you.
Okay, thanks a lot. So in odd dimensions, crucially, sphere partition function of a CFT doesn't have log divergence. And that means that the finite piece, once you subtract off the powers, is well defined. So this assumption is automatic in odd dimensions. But in even dimensions, as you can learn from this nice paper of Zohar Komagotsky and Jaume Gomez and Gershkovitz, generally, there'll be a log divergence, which means that the finite piece left over is sort of fundamentally ambiguous. But if you assume enough supersymmetry, you can make it unambiguous. There's some manifestly supersymmetric scheme where this thing just becomes well-defined. So in 4D, n=2 is enough. And in 2D, n=2, is enough. So these are kind of sufficient conditions for what I'm going to say to apply.
So this ambiguity is not just the conformal anomaly.
No, it's like the conformal anomaly is the log divergent piece, and the ambiguity is like the finite piece.
But it still is proportional to the conformal anomaly.
It's a scheme-dependent part of
It's scheme dependent.
It's scheme
You can shift around with the counter term.
Yeah, if you like rescale the UV cutoff, you'll shift this piece.
So that's the part of the anomaly that again that can be changed by
Yeah, so not the C, not the A, but some
the
additional.
box.
Local counterterms.
The box R,
Yeah.
yeah.
Makes it non-ambiguous.
Sorry?
Some scale has to come in, right? So it's like log Z over something, makes it non-ambiguous. What scale?
There's the radius of the sphere.
Yeah. So the log term is like log of radius of the sphere over A, which A is the UV length scale. Okay, so this is kind of domain of validity of what I'm going to say. It probably looks like basically we're talking about supersymmetric CFTs. Although that's not
supersymmetric regularization scheme.
Yeah, I mean that's not. I'm not putting that in for odd dimensions, but we don't know any examples. Okay.
Well, for like well, okay, yeah.
No, go ahead.
There's probably some kind of non-local.
Non-local, yeah. Probably I should. Yeah, we can. It's an interesting question. Okay, so then the results. So I may assume that like the theory, the whole conformal manifold of theories may have some symmetries, right? Like supersymmetry. And so they may have some R symmetry, something like this. And so I may have some quantum numbers that characterize all the states in this space of CFTs. So I'm going to say that for any quantum numbers, let delta be the dimension of the lightest unprotected scalar. then delta is a concave function over the conformal manifold. But as we already saw, this statement is vague, right? Because you saw that changing coordinates in this lambda goes to square root lambda changes whether it's true or not. So I need to say what I mean by concave. So I'm going to say, with respect to, okay, I'll just continue here. With respect to a dressed metric, which I define to be, I'll call it G tilde. So GI are the exactly marginal couplings of the theory. And I define this to be the product of the sphere partition function and the usual Zamolodchikov metric. I'll state the definition of that later. So you see why I needed to assume that this, I'm talking about the finite part here. You see why I needed to assume that it's unambiguously defined, otherwise this would be kind of ambiguous statement. And I'll say what this concavity with respect to a metric means in a minute. Well, that's the statement. And
unprotected just means not annihilated by any supersymmetric.
yeah, I was going to say that in a minute. So yeah, unprotected. So for me, protected literally just means constant. So any scaling dimension which is constant over the conformal manifold, I'm calling protected. And ones which are not constant are unprotected. So I can also give a more general statement. So more generally, within a given sector with fixed quantum numbers, within any sector, the sum of the lightest n scalars, scaling dimensions, is concave. This is how you prove the statement above. Right? So you see that this implies this, because if you take the first n-1 to be constants, right, then and take delta n to be delta, then you're dealing with the lightest unprotected scalar. And this statement just implies that the delta is just concave. So I reminded myself to explain what certain things mean. So here I'm just counting each conformal multiplet once. Right? I don't count primaries and their descendants separately. But in the case of spinning primaries, which may appear in this sum, I count the first scalar descendant. So for a spinning primary, with indices, I would count the dimension of this operator in this sum. Okay.
Okay.
It's just the sort of first scalar operator that appears in the multiplet. And so, as you mentioned, there can be level crossings and things like this. So strictly speaking, what I'm saying applies away from level crossings. At least I need that the sort of nth guy isn't sort of which operator is the nth operator shouldn't change. I can have degeneracies in the lower operators, that's fine, as I often have in SUSY theories. So let me define what a concave function is.
Okay, sorry, just your conformal manifold is a manifold, or can it have singularities?
You can have singularities, but what I'm saying is true away from the singularities. Yeah. This is really, it's really a local statement, right? So, yeah. And indeed, something singular can happen at singularity. So this function is a function of the over the conformal manifold is concave with respect to this dressed metric. If its covariant Hessian is negative definite. Okay. But it's a very simple generalization of what we normally mean by concave. But just bear in mind, these are here the covariant derivatives with respect to this tilde metric. And an equivalent, but practically more useful way of saying this is that for any geodesic, GI T, the second derivative with respect to the geodesic parameter is this. Right, so geodesics are parameterized by affine coordinates, and the space is kind of covered by geodesic. So you can we'll use this definition in practice.
In the n=4 example, is the statement still true if you include the theta angle?
It's a bit hard to check because we don't have a lot of data.
Oh.
So
Or
Like at
is it-
finite n, right? We don't know a lot.
Ah.
But I think, yeah, it's a good question.
For the bootstrap, they have plots also for the theta direction. Just
Yeah,
the theta
but they
dependence
don't
is
have
very
a lot
weak.
of-
It's very weak.
Yeah, it's very weak dependence. I wasn't sure, like, yeah, how much I can trust that this is
Mhm.
like it's saturated roughly, but like there's some numerical error, and
Yeah.
so I didn't like look at it very carefully. But actually, from my qualitative checks, I think it looks correct.
But it like that would fall from your.
So the statement is for any geodesic. I'll make precise statements about n equals 4 later. But yeah, indeed, you can take any geodesic with respect to this metric on the fundamental tau domain, and the claim is that you'll have a statement of concavity. So of course, like the motivation is probably clear that conformal manifolds are very special, right? The presence of a conformal manifold should drastically constrain the theory, but we don't have a very good way of understanding these constraints. Like, how can I use these constraints for the bootstrap? Some rules have been written down to try to characterize the presence of exactly marginal operators, but I think we don't know how to get like all the juice out of it. So here we're really making some statement about moving around the conformal manifold. And also it helps us to learn a lot about unprotected operators in superconformal field theories. Even in n equals 4, the simplest case, at finite n, we know extremely little. We basically just have these plots from the bootstrap, and that's almost like all we know. So anything we can get, this is quite a general global statement, seems like a progress. And of course, also, it feels like we're in ADS CFT, we stand to learn something about moduli space of quantum gravity by thinking about these kind of questions. So I'm very interested to kind of understand how this relates to swamplandy questions about gravity. So it's kind of nice to notice that convexity of lowest eigenvalues of operators is a completely generic phenomenon. So this is totally natural in the sense that, like, if I start taking some positive definite operators and I define kind of convex combination of them, which is then also positive definite, then the lowest eigenvalue delta, let me just call it delta, is concave over T. This is a very generic statement, mathematical statement, for a certain class of operators on Hilbert spaces, let's say. So, you should expect that as long as we can find a kind of way of treating the coordinate dependence that amounts to taking linear combinations of dilatation operators, you should expect that something like this is true, right? And of course, we also have examples in CFT where we know that there's convexity. So like the main kind of example we all know about is the leading Regge trajectory has been shown to be concave. So this is the lowest dimension operator with a given spin, the concave function of spin. This was shown, there are lots of interesting papers about this, but the reference I'll give is Zamolodchikov and Zhivaedov. And another example is the charge convexity conjecture. So this is due to Aharoni and Balti. And the claim here is that the lowest operator with a given charge under a global symmetry of the CFT will be a concave function of charge. I think that this is believed to be sort of true in some sense. Perhaps there are some exceptions that have been found, but at large charge, at least, this is expected to be true. So, this statement kind of fits in quite naturally with the things we already know. So let me begin. There's so many blackboards, it's kind of like dealing with a geometry problem.
Yeah.
Rather confusing.
Try not to use the one in the very back because that one cannot be moved.
Okay, very good. So let me begin. So this one's okay.
Yeah.
Yeah, okay. Let me begin by reviewing a little bit about conformal perturbation, which is going to be our tool. And for me, the nicest reference about this is by Tasov. Also nice papers by Zamolodchikov and Cardi. So we're dealing with CFT on the e-dimensional sphere. I'm glad I don't have to explain what e-dimensional sphere is, as in the previous talk. Hard. And so, for example, I can use these coordinates, stereographic coordinates, for dx squared over 1 plus x squared over r squared squared. So r is the radius of the sphere. These are nice because I can sort of basically do computations in the plane. And the action, well, we don't need to have an action, but like schematically, you can think that we have the dependence on the marginal couplings GI, like this. And I'll denote the marginal operators by Li. Lagrangian, for example, would be 1 in n equals 4. So I'm going to be thinking about going along a GD thing, right? So bear in mind that in practice, we'll think of GI as some path in space of GI is parameterized by T. An important object in the game here is the sphere partition function, the expectation value of the operator 1. And I'm going to define correlators as non-normalized. Okay, I'm not normalizing my correlators, slightly unconventional. I'm going to take these guys schematically to be by this. Everything's always depending on G, right? I won't write G, but it's the action depending on the coupling. So then it's actually these correlators, non-normalized ones, which have like the simplest dependence on marginal couplings in conformal perturbation theory. So these guys, when I take a T derivative along some trajectory in the coupling space, these guys just transform in the simplest way. I just insert an integrated marginal operator. And so you see what will happen here is I'll get sort of contraction of the marginal operators with the derivative of G. I'm going to use this notation, dot is d by dt. This is the derivative along some trajectory. This is the conformal manifold. I'm going along some trajectory. Okay, parameterized by t. This is the space GI. Okay, sorry. And I'll often abbreviate this just to like G dot L. Okay. So one comment here is you might worry that these operators actually can depend on T. It has some internal dependence on the couplings. But I can always move that into contact terms. So my prescription is going to be I never write down explicit derivatives of O. You can always put a contact term between L and O, which just reproduces whatever you want to put. So that's going to be our sort of frame of choice. So now let me consider the quantity that will be important for what we want to say. It's the two-point function of this lightest scalar frankly. Okay. I can normalize it so that it's given by just this power of R, where R is the radius of the sphere, and I put points at 0 and infinity. So that's like in the sphere, it looks like antipodal points. Okay. So the idea is going to be to take two derivatives of this quantity. We'll get an integrated 4-point function, and we'll try and say, well, that sounds positive, right? Integrated 4-point function. And so we'll get some kind of positivity constraint for the second derivative of the scaling dimension. But first, let's think about the first derivative. So we're actually going to take derivative, or we'll take log first, and then derivative. Take log of this, and then its derivative with respect to t. And so I just follow conformal perturbation theory. I get minus O integral G dot L. I won't write the gamma explicitly. Okay. And then downstairs I just have 2. On the right hand side I get minus 2 delta dot log R. Okay. So it's instructive to just spend a moment trying to understand how the left hand side can give the right hand side. So let's do that. So we're going to need to know the relevant OP. So it's about the OP coefficient between OO and L, right? So let's write down G dot L. So this contraction of the marginal operators with G dot. And we'll take its OPE with O. So this contains terms like C G dot L OO, OPE coefficient, 1 over y to the d, and then O. This is the one we care about. But there's also a contact term. Because this is dimension d, you can write down a delta function with the same dimension. So I'll denote contact terms by gamma. This is the general form of the terms we care about. So you see, I plug this in, and of course, this integral diverges. When diverges logarithmically, when the marginal operator hits one of these primary operators. I need to regularize. So the strategy is going to be to regularize. And for us, that's going to be excising some balls of radius A around 0 and infinity. Okay? And what that means in practice is that we replace this guy, this integral over over y with an integral on the domain where modulus of y is between a and r squared over a. So in these coordinates, this r squared over a corresponds to this ball of radius a around infinity. You can see that by just applying this inversion map to this cutoff. So a equals uv length scale. Okay. So I have to regularize. This one is.
Oh, you can just exchange the two.
Yeah, let me just see this one.
This is not breaking any of the spherosymmetry.
Sorry?
It's not breaking any of the manifold spherosymmetries. This regularization is it breaking any of the manifold spherosymmetry?
Yeah, it breaks conformal invariant.
But that's
But I'll explain. Let me explain that. So the strategy is you've got to regularize, but this screws up the answer, right? Because you're going to get some answer which depends on A. Now, it'll depend on a ratio of scales for radius of the sphere and A. You need to cancel the A dependence by tuning the contact terms. Right? You can't tune OPE coefficients because they're physical. Contact terms are sort of scheme dependent. You can tune them. They can depend on UV cutoffs and stuff. So the strategy is to first regularize, and two, tune contact terms. Okay, this is important. So you do this, you compute the integral. You can actually compute these things in flat space because it's a ratio of correlators, it's Weyl invariant. You just do the computation, and what you find on the left-hand side is minus the left-hand side equals minus 2 times the OPE coefficient times log of R over A. There's also some angular volume factor, we put alpha D. But so you wanted to make a log of R, but because you put this UV cutoff, you put this A dependence. But now we also get a contribution from the constant term, which is 2 gamma times, just 2 gamma. Okay. So now it's obvious what you have to do. Right? This gamma, its canonical choice is that it doesn't depend on R. Right? So you should take, to make this equal the right-hand side, you should take the OPE coefficient to equal 1 over alpha D delta dot. Okay? And this gets the right log R dependence. And you should take the contact term to equal whatever is needed to cancel this log A. So it should be something like delta dot log A. Not sure about the sign. Minus. Okay, so is that clear? This reproduces the right-hand side, right? Because now this equals minus 2 delta dot log R. So this is how these computations work in conformal motivation theory. Any questions about this? Okay, so I'll come back to this formula later, because I'm going to want, as I said, to take another derivative. That's how we'll get this second derivative being negative. But now let's carry on and let's think about another quantity, which is going to be important. And what I'm doing. So let's think about replacing this primary field, O, with the marginal operator itself. Let's think instead about this guy, GL, G dot L. So this is the generator of T translation, G dot L. So what's typically defined as Zamolodchikov metric is this guy. But maybe let's get rid of the G first. So let's have IJ. These are the marginal operators. So this is the Zamolodchikov metric divided by R to the 2t. Okay. This is just the definition. So it's normalized. So now let me contract with G dot. So I'm going to be contracting this guy with G dot, and that's the same as writing the TT component along this trajectory in the conformal manifold. Right, so I'm going to look at the components along this trajectory. So that's what I get when I contract with G, the G dots. And I can multiply it by this partition function. But this quantity, the product of the sphere partition function and the Zamolodchikov metric, is nothing other than my dress metric, which I defined it. Okay. So it's the dress metric that appears when you consider this quantity with these unnormalized correlations. And now I'm going to play the same game. So I'm going to take log followed by a t derivative, and I'll instead get 3 marginals divided by the 2-point function. And now you see it. D is fixed. So I don't get a log on the right-hand side. I just get the derivative of this guy. Once I'm taking log, I get log derivative. But a dot means t derivative. That's what I get. So basically, this tells you that the 3-point function between the marginal guys, so the 3-point, we say the OPE coefficients, between 3 exactly marginal operators is 0. This is a very well-known fact for exactly marginal operators. And yeah, now the contact term between these guys has to be tuned to reproduce the right-hand side. So it's proportional to this logarithmic derivative of the dress metric. Okay. So what we're actually going to be doing in what follows is sort of making sure that this right-hand side is 0. Because such a contact term would actually screw up the argument in 1 second, in what follows. So bear in mind that later we're going to choose coordinates, right, so that this quantity is 0, which is just the same as going along a geodesic. So when we go along a geodesic, we'll be setting this quantity to 0. Yeah, what's your question?
I answered my question.
Okay.
No.
Thanks.
Sorry.
Any other questions? So now that we come to proving my statement, let's talk about concavity. So I'm going to prove it, explicitly in the simplest case. So I'm going to assume a 1D conformal manifold, so just one exactly marginal coupling. And I'll talk about the generalization later, which is in hand. There's no funny business. I know how to do it. And I'm going to deal with just the lightest operator, lightest scalar. So it's not the lightest unprotected scalar yet. It's just the lightest scalar. But I also know how to make this generalization. I'm not doing a sum over states. Over scalar dimension is just the lightest one. So we had this quantity. I hope I didn't erase it. Yeah, this thing. This is the first derivative of the 2-point function of O. Let's take another derivative. So now what I get is OO integral of G dot L squared divided by OO. And these are always at 0 and infinity. But I get another term where the derivative hits the 2-point function from downstairs. I get minus OO G dot integral G dot L over OO squared. That's what I get. And this equals minus 2 second derivative of delta log R. And this is the thing we want to prove is negative, right? So this is a variance. This is the variance of the operator I, which I define as just the integral of this thing, in the O state. Okay. Maybe that's not quite explicit enough. If I define expectation value as this, sometimes I won't write the O explicitly, so let me just write it like this. If I define expectation value of I as OIO divided by OO, this V is the expectation value of I minus expectation value of I squared. Or if you have complex operators, it's omission squared. Okay, so this is positive. They put a question mark because it's UV divergent. You need to do it carefully, and that's what we're going to do. But this is just the spirit of the claim. This is a positive quantity. It's a variance. Okay. Yeah, so it's UV divergent. That's the problem. This argument is not sufficient and would give you wrong answers sometimes. So it's UV divergent, so you need to regularize. And the spirit is like the same as before. So there are different kinds of divergences, and some of them are really easy to handle in a positive way. The divergences where the marginals hit primaries is easy because they're symmetric. They're like reflection symmetric. Right? There's some reflection positivity that makes this work, and I can just deal with those by changing what operator I put here. I just define a regularized operator where the integral goes, we write it like this, the absolute value of y goes between a and r squared over it. I just cut out balls around the O operators. Yes, sorry. So I just define this guy, and it looks like I'm kind of good to go for those divergences. Right? So the idea will be to sort of, again, consider the same quantity, just variance of this regularized guy, and to hopefully claim that this is positive, and to learn something about the right-hand side. Okay, so we still have to be careful. So the picture is like this. I've cut out little balls around 0 and infinity, but I still have these marginals integrated everywhere. That's one of them, and this is another one. So they collide with each other, and this is another singularity which you need to worry about. So let's now worry about the LL singularity. So the quantity that contains this singularity is this one, right? O, write it properly, O0, O infinity, integral d dy, g dot L, y, integral d dz, g dot L, z. Okay, and I have these, I've already replaced I with IA. Okay. And this quantity, by the way, was studied already in various works. For example, Konogotki and Simmons-Duffin studied this guy. Also a paper of Rastelli and Richkov, Konobehan, and Bernard Uzan. So this quantity, you can read about it. And for example, one thing you can read is that you can use conformal invariance to write it like this. I can pull out a kind of overall scale, the position of this y variable, basically. So I get d dy over y to the d, again integrated over this range. And then what's left will be, well, I'm kind of fixing the first marginal to 1. That means like 1, 0, 0, 0, 0. And then I have the position of the remaining marginal guy still to integrate over the integral dv u. I call that u. This is like z divided by y. Okay? And so there are different regions of integration. And in different regions, different OPE channels are convergent. In fact, each OPE channel converges almost everywhere. But if you just use one, you don't really see clearly the singularities in the other channels. So you'll screw up like the contact terms you need in the other channels. But what we care about is this channel. Okay, that's the singularity that's the only singularity that's left. So that means that these guys are going to be contracted. So let me replace the product of O's with their OPE. Okay, so I'm dealing with a region where U is kind of near to 1, let's say. I just replace the product of O's with their OPE. So I'm summing over all operators, O delta tilde. So the first comment is that for spinning operators, O delta tilde, the principal value description for this integral is 0. And that's the one we'll take. So I think there's a sort of natural sense in which spinning operators don't contribute. And this is just by rotation symmetry. Now, for generic scalars, like the presence of exactly marginal operators just rules this 0 for generic scalars. And that's because this one, this quantity here, starting from the integral over u, in the case of a generic scalar, O delta tilde would be this, which is just minus the derivative of the 2-point function between O delta tilde and a marginal operator, g dot l. But that's 0, right? These have different dimensions. This has dimension d, this has some other dimension for generic scalars. So conformal perturbation theory just tells you to throw that away. Okay, I'm being a bit quick with this, but these things just don't contribute. The ones that you need to worry about, ones that can mix with L, are the identity operator. Actually, on the sphere, that the marginal operators can mix with identity, and marginal operators themselves. So identity operator. This thing is just kind of rendered finite unambiguously by the sphere partition function itself. Because the identity contribution, you just plug in identity here, and what you have is integral over z and y of a 2-point function of marginals. But this is the second derivative of the sphere partition function. What am I doing for time? Okay, it should be done. Okay, so this guy is just controlled and rendered finite, sort of unambiguously, assuming that you unambiguously know this guy. So now here's the one we actually need to be careful about. The marginal operator itself. So we're in the 1D case where I only have one marginal operator, one exactly marginal operator, 1D conformal manifold. In general, you need to use the geodesic equation to show that the other operators don't appear. That's what happens. But so I just treat this one operator. And the contribution there goes like this OPE coefficient that this is some OPE coefficient. I still have this integral over y, regularized. And now I have a quantity that we put in a box earlier. It's a 3-point function of marginals, with one of them being integrated. Okay, so we said earlier that this basically, the OPE coefficient is 0 between 3 exactly marginals. It's just a pure contact term. And we said it's proportional to the log derivative of the metric, of the dress metric. Okay, so let me write that down. This guy is proportional to GTT tilde dot over GTT tilde. This guy is just a log. You just compute this integral, proportional to log R of A. And this guy actually we wrote down earlier is delta dot. Okay, so if such a divergence is there, your logic is a bit screwed up because this V of IA doesn't really exist. It has a divergence in it. This is a log divergence coming from a contact term between when the L's hit each other. So if this term is present, you're maybe in trouble. You're dealing with some divergent quantity. Over here. But now, as I said, along a geodesic, in 1D that just means taking t to be the affine coordinate. So that's the coordinate such that T tilde is constant, its derivative vanishes. This term is absent. Okay, so along this trajectory, this guy, the variance of IA, it's sort of finite, and all the divergences are kind of unambiguously resolved by the things you know. One sec. Hang on. I'll justify this a little more in a minute. But the log divergent piece is that, sorry, of the second derivative that you want, there's a remaining piece, which I'll call D, which doesn't contain logs. Let's say that's how it's defined. Now, you look at this D for a minute, and you want this D to be finite. If D is finite, you can use this statement to conclude that this second derivative is negative, and you're done. The only divergences in D are power divergences, which come from the other OP channel, and they come from exchanging operators lighter than O. So if O is the lightest scalar, as we assumed, this is finite. This you can just check. So this implies that the second derivative for the scaling dimension is negative along this GD. Okay. Let me state the proper version of this before I open up for questions, which may just ask about what I'm about to say. So let's do it more properly. I have a lot of time. But to do this more properly, what you should do is define a quantity, which I'll call V a reg of I. And this one is just UV cut off in the normal way. Cut out balls between all operators. So this is like, what we were doing so far is kind of weird UV regularization. You only cut out some balls. Here you cut out balls everywhere between all operators, between the L's. So this guy is manifestly finite, and it's a standard regularization. So for this guy, you believe that you correctly, that it captures the log term, which is supposed to be universal, in the quantity you care about, right? Which is V of I. But this quantity is bad in terms of positivity, because it has power divergences, right? Like when the marginals hit each other, this guy will have all kinds of power divergences that get resolved in the other regularization, which are not sign definite. So this guy is not good for concluding anything about positivity. But what's nice about this guy is we can precisely track the relation of our log term in our quantity to this one. The only difference is this contact term. You can just check that's the only difference. So if you just compare log terms, you see that what actually goes wrong with this quantity, if you choose a different coordinate, so if you don't go along a geodesic, what actually goes wrong is that Vi of A, it picks up an extra contribution. So as well as the term in this properly regularized thing, you pick up another contribution from this contact. And you can really trace that's the only difference between these log terms. Now, what actually goes wrong if you use a different coordinate system? You see, to identify this actually, this is the affine connection in the T variable. So this is nothing other than the statement that this lowest scaling dimension is covariantly concave. So this feels like a smoking gun that you did it correctly. You did all this stuff with contact terms, feels very messy, but you got a covariance statement in. So this is kind of proper way of doing it, but that way above is just like going on a geodesic and seeing that connection coefficients sort of not there. Okay, before I move on, questions?
What about operators of dimension D minus 2? Yeah, curvature. They could mix with operator of dimension D to curvature, right?
Yeah, perhaps I need to assume something like no integer gaps. Except between protected operators, I'm happy to assume things that like, I should think about it more, we should discuss, but I'm happy to assume things like, you know, say I have a bunch of protected guys, and I'm trying to talk about this guy, which is unprotected. I'm happy to assume I'm not near the place where it gets an integer gap. And I can just kind of continue through that place. That's kind of good enough, I think. But yeah, I think it's a good question. I haven't really thought about it enough. But yeah.
The question that Gabriel asked is relevant when you apply to the 1402 examples, because in those examples you didn't discuss, but when you put on theory on sphere, when you want to have this sphere from the function that's unambiguous, you also
Yes.
have to turn on background for the R symmetry. And then once you have done so, there are R symmetric operator that, you know, like current non-trivial R chart can mix with your operator.
Yeah, this is a good point. Yeah, indeed, there is some kind of residual ambiguity even in like 40 n equals 2 theories.
Yeah.
But I think with localization, you can get it. I mean, you know the precise mapping between Lagrangians and like sphere partition function. So I think there's a kind of ambiguity, but you can like just fix it once and for all. But then your conclusions probably do depend on the choice.
Yeah, I think my question just that the related question is that when you look at on sphere, it's not just a background for the metric.
Yeah.
You also turn on R background.
Yeah, indeed. Yeah, we should discuss it more. Maybe I continue for now and we can discuss at the end. Yeah. Thanks.
Question.
Sure.
I'm still a little confused about what happens when you have a let's say a periodic direction in your conformal manifold. Is a corollary of what you're saying that you must incur level crossing if you have a periodic direction?
You feel, yeah.
Oh, is that known separately or?
I mean,
I was gonna ask this question too, but
Okay,
yeah.
that will be a corollary.
right, because
Yeah,
there's no way you can have a concave function.
Yeah.
Sure. So one thing is that
domain.
the geodesics of this in n equals 4 case, I'll come to it in a minute.
Yeah.
They're like radically different than the geodesics of the Zamolodchikov metric. I think they don't really have these loops.
No, they definitely do, right? I mean, I can have a geodesic pointing in any direction, so I could choose.
Let's come to it in a minute because I'll draw this fundamental domain and we can discuss. But you know, there are these statements that, but firstly, people say that this moduli space should be non-compact. And there is a kind of general sense that like you don't have concave functions, convex functions on compact manifold. So these things kind of rhyme, but I don't have a very precise sense of what's going on. But yeah, indeed, maybe if there is some compact cycle, if a geodesic can go around a compact cycle, then there should be some level crossing or something that screws this up. But
The 2D B field certainly would be one example.
Yeah. Or
According
the
to
or the
what
Z
is that?
angle and
Yeah.
angles.
Yeah.
in 2D SUSY theory,
Oh, and also the then going into function parameters. Yeah.
um,
In 2D, not necessarily supersymmetric, just compact
Compact
boson, two
boson,
compact
yeah.
bosons, you have B field, right? Periodic. It's like the theta angle.
but that doesn't meet my assumptions for the partition function. For these,
You can take the supersymmetric ones, yeah.
yeah, okay.
Yeah, the supersymmetry in that case does not change the couple manifold. Just to take two complex boson paired up with two
Yeah.
fermions. It's the same couple manifold.
Okay, yeah, we should discuss this example. Yeah, good. Great. Thanks. So this was the simplest case. Let me just comment verbally about generalizing to the general case. So you want to have a multi-dimensional conformal manifold. And as I mentioned earlier, the way to argue for this case is just to go along geodesics, apply the 1D argument, and use the geodesic equation to basically play the role of this affine parameter. To argue that sums, by the way, I didn't say this before, but actually for this thing about combining dilatation operators, that linear combination, it also tells you that the sum of the lowest n eigenvalues is concave. So that's also very natural. So to get this statement, you basically need to do a kind of matrix version of the variance, which will be a positive definite matrix. This quantity basically sort of tells you that the sums of lowest operators will be concave. And finally, we want to restrict to a superselection sector with fixed quantum numbers. That means that we kind of get an infinite number of operators we can talk about. And the way to do that is just to use charge conservation. So the point is that these power divergences, that would stand to screw up the statement if you had lighter operators, they're just absent if by charge conservation, if you're dealing with the lightest operator of a given charge sector. Okay. So this is all handled. Modulo these issues that you rightly ask about.
Can you say a little more about saturation?
Saturation.
What you call it? Energy saturation?
What do you mean saturated? Sorry.
Inequality, like where does it become like a
Yeah, okay, yeah, that
point?
let me discuss n equals 4 where I really have a better picture of how things work, and then I can give an example. You mean when it equals 0?
Yeah.
Yeah. So let's go back to n equals 4, which was our kind of starting point. Equals 4 supergammules. And as I said, we need to be at like finite. We want to have a proper CFT, finite central charge. We'll talk about the planar limit in a minute. So the coupling constant, the marginal coupling, is the complexified gauge field, which is basically theta angle and Yang-Mills coupling. And you should think of this as living in the fundamental domain, with the edges identified appropriately. So this is, we want to mod out by the duality group. This is like upper half plane mod SL2Z S duality group. But I think that this is the space of true CFTs, not H, but this quotient space, and this is the place where our results apply. So you can really think of folding this guy up, making this some space, and so as for any for the n equals 2 theory, the Zamolodchikov metric is scalar, which follows from n equals 2. So it takes this form in terms of the Kähler potential K. And in this case, it's given by 2 n squared minus 1. N is the number of colors, divided by imaginary part of tau squared, dt pod. So, and this is where the ambiguity comes in, but I think that there's a sense in which the right value of the Kähler potential on this domain here is this one, -8 n squared minus 1 log in tau. So then Komogorski and collaborators told us that in 40n equals 2 theories, the four-state partition function is given by e to the k over 12, which in this case is imaginary part of tau, the power -2/3 n squared minus 1. So now you have all the ingredients, you can write down this dress metric. Detailed one. So it's the product of the fourth-bit partition function and the Zamolodchikov metric. So it's given by 2 n squared minus 1 dt bar divided by imaginary part of tau. So the 2 plus 2/3 n squared minus 1. So it's easy to tell looking at this metric that theta equals 0 is a geodesic. There's a reflection, for example, in theta equals 0, reflection symmetry. And along that geodesic, the 1D induced metric is d of Yang-Mills to the 2/3 n squared minus 1 squared. So this is our affine coordinate, t. So here we're going along this geodesic. So yeah, this is kind of a punchline which I have left right at the end. So the statement that this predicts for n equals 4 is that the lightest unprotected operator is a concave function of this sort of funny looking power at Yang-Mills, which depends on n. Okay, and this is true, at least according to the data we have. So this is this plot from Shai, Chester, and collaborators. Looks like this. This is the other. This is a SL2Z image. This region. And it's actually something much stronger. It seems to be true, just empirically. It's a concave function of Yang-Mills squared. This implies This implies what we want to be true, what we predict, because this guy is always greater than or equal to 2. Okay, so it's the right way around. And it's not saturated for general values of NC, but it's saturated for n equals 2, the minimal case. So in n equals 2 case, like what we have is we have like the lowest power that's allowed here. And this kind of, I guess, addresses your question partially. So sorry, I already drew it. So at this point, this is a plot as a function of g angles squared, which is the affine coordinate in n equals 2 case. At this point, the claim is saturated.
So how equalize the maximum of delta?
Yeah, so yeah, that's my next. I know I'm kind of. I have 5 more minutes. Is it okay?
I'm not sure.
Yeah. This looks a bit funny, right? The power depends on n. It's a bit like, what should we make of this? You might object that you think this looks like a funny power of g angles. But what's cool is that you can actually extract at least in these like n equals 2 theories, I believe, and definitely for n equals 4, you can actually extract monotonicity from this statement. As you pointed out, there's a maximum. So I believe this probably generalizes to, well, n equals 2 theories that have SL2Z, S2LZ. So you expect, and I think you'll all agree, that the scaling dimensions should be smooth functions on the whole upper half plane. Right? You go to these points like tau equals I, you don't think some cusp is going to appear in the scaling dimensions. And you also expect that they transform in representations of SL2D. So at worst, what can happen when you go from one domain to the other is that the operators get sort of permuted.
Sorry, N is the upper half plane?
This
or
is
fundamental?
H upper half plane, yeah.
So why do you expect it to be smooth?
Well, I mean, I think what we observe is that when maybe you tell me if I'm wrong, but if I go through tau equals I, I have a picture like this is g angles squared. It looks like this. It just goes back onto itself.
Right.
What
About 4 pi. But I didn't see like a cusp here.
What about tau equals e to the 2 pi I over 3? Second orbital.
That's the particular case. But now you're making a general statement.
Let's say I take this as an assumption.
Uh-huh.
But okay, maybe sometimes this is not true.
Mhm.
Yeah, we should discuss, and you should tell me if this is like not really realistic assumption.
In this example, I think in Silvio's example, if you also look close to, theta is like 2 pi over 3.
Yeah.
It's the same feature.
It's smooth.
Yeah.
Oh, okay.
Yeah,
Theta equal to 2 pi over 3, and you just.
I thought this was kind of a generic feature, but maybe it's not.
Well, this is linked to first parameter.
Yeah, maybe I'm just. Yeah, it's a strong assumption. Let's say. Okay, let's take this as an assumption for a minute. If you have this property, then you can say that my statements are a bit singular as I go across from the fundamental domain to this image. As I go across self-dual points. But whenever I go through the boundary, there's a scalar transformation that relates K and relates to this sphere partition functions. So the affine coordinate changes. I have like some T and T prime. There's some non-trivial relation between them. But what happens is something like this. So below 4 pi and above 4 pi, function is the same. This is like trivial representation of SL2Z. So that's allowed. And it's also allowed that there can become degenerate with some other state and they get permuted. Okay, that's also allowed. But what's not allowed is something like this. This would still be locally concave, but you get a sort of minimum where there's a cusp. This is not allowed because of my assumption about smoothness. Because the relation between these two parameters, T and T prime, it doesn't have derivatives that blow up at this point. So this would not be allowed. So you see, this would be non-monotonic. But on this fundamental domain below 4 pi, these are monotonic. So yeah, assuming this perhaps quite strong assumption, I conclude that the lowest unprotected scalar is monotonic on G Yang-Mills squared below 4 pi. And this statement has a smooth n goes to infinity limit. So it becomes the statement that what starts off as the Konishi operator and becomes this double trace, which gets protected in the large n limit, is monotonic. So that's kind of nice. But we thought a priori we might have thought it could have some little wiggles or something, but it doesn't. And now here I've used SL2Z to prove monotonicity in a kind of SL2Z-ish way. But I gave you this kind of motivation at the beginning that you may think you could get in holographic theories more generally monotonicity in the planar limit. And the idea would be, yeah, in the planar limit, these double traces become protected, and I can identify a trajectory that goes through them. And this is like the lightest unprotected operator. It's Konishi in equals 4. And I would want to say, yeah, well, it has to be concave, as a function of some affine coordinate. And I know that its first derivative is positive at the end because it's blowing up. So then that implies that its first derivative has to be positive everywhere. That would be the spirit, but in practice I can't quite do this yet, and I'm still thinking about this because where I can actually work is at large finite, where the picture looks different, right? Instead of this, I have level crossings that sort of closely approximate this picture. So really, I'm kind of stuck dealing with this guy. But you may think you can kind of stick together the argument in this region and then this region one at a time, show that each bit is sort of forming a concave function. But I think to really make that precise, you need to understand kind of the uniformity of the n goes to infinity limit over lambda in a way better than I currently have understood it. So that's something I want to work on in the future. Sorry for running over time, but let me just summarize verbally. So I've shown under certain assumptions that the lowest scalar operators in CFTs with exactly marginal couplings and a well-defined sphere partition function are concave with respect to a dressed metric. This is kind of interesting quantity. And in n equals 4 theory, it showed up under some assumptions, which I think may generalize to a class of n equals 2 theories, using S duality, that the lightest unprotected scalar is monotonic on the fundamental domain, along a particular geodesic. And in ADS CFT, I think that these properties say something possibly interesting about the moduli of quantum gravity in ADS vacuum. And so there are lots of interesting open questions. So one is the relation between this story and the song plan, so particularly the distance conjecture. In some sense, at this point, Yang-Mills equals 0, this statement of concavity feels like kind of opposite to the distance conjecture, which says things have to blow up fast in a different coordinate system. There's some tension between them, but they're both true. So they're sort of like opposite, some kind of opposite statements, which are both true. But I think that there's an interesting relation to distance conjecture. I'd like to understand better whether an argument like this can fly. So in holographic theories, this convexity may lead to some monotonicity. Question mark. In n equals 4, various special things happen. So we saw in n equals 4 that these things are actually concave functions of Yang-Mills squared. So it's much stronger than the property I can derive. So it'd be interesting to understand if that can be proven. I guess the point is I'm not inputting that much information about n equals 4. So like I don't know, this doesn't know everything about that theory. And another kind of miraculous thing is that I'm only talking about the lighter state, but in n equals 4, all the single trace operators appear concave and monotonic. So probably what's going on there is in the planar limit, integrability takes over. And the level crossing is kind of telling you that integrability sees all the states as being in different superselection sectors. Right? It can kind of trace them all and distinguish them from each other. So in a sense, it feels natural that these power divergences don't screw things up for heavier operators. And yeah, it would of course be nice to generalize this for spinning operators instead of scalars. I believe that probably works, though I didn't do it explicitly. And finally, it would be very nice to think about defects. So in particular, the defect scaling dimensions in the supersymmetric Wilson line, n equals 4, also look concave and monotonic. And I wonder if some expectation values of Wilson lines are also concave functions.
These are dimensions of the function of the bulk couple.
Yes. So sorry for running over time, and thanks a lot for your attention.
So let me talk. I was gonna ask a related question to the defects, which is instead of considering some fixed defect and then varying the bulk couplings, you could consider a defect which has some exactly marginal parameter on its roll volume. And then you can ask about whether there are any concavity statements you can make. Have you thought about that at all?
What would be an example?
Oh, let's see, what's an example?
Broken symmetries in the
any-
bulk, for example.
They have tilt operators on
Yeah.
there.
Would scaling dimensions depend on these things?
They should,
They
yeah.
will depend, yeah.
Then that seems kind of easier than bulk couplings.
Yeah, I think they're easier.
Bulk couplings, you have like some different divergence structure.
Yeah.
Yeah.
But that will be kind of more analogous to what the Nat was doing directly on the defect.
Yeah, agreed.
So you think it'll work? I mean, because
I expect it may
we were
work, yeah.
complaining a little at the beginning that somehow we only have supersymmetric examples of
Yeah, that
conformal
was-
manifolds, but in the defect world, there's sort of everywhere, and you don't need supersymmetry.
Yeah, I guess the thing that could screw you up is you need an analog of this unambiguous sphere partition function, which in
Yeah,
that case would be like probably unambiguous vacuum defect, like expectation value of the defect.
Yeah.
Which in principle maybe is not controlled.
Yeah, if it's odd dimension, it's fine, but for you,
Yeah.
so in that case, you
Odd
can
dimensional
have,
defect.
you can have odd dimensional defect without supersymmetry with couple manifold. There are tons of examples,
Ah, cool.
unlike in the bulk, just
Yeah.
coming from broken bulk symmetries, bulk
Okay.
global symmetries.
Okay, yeah, I should think about these examples. It would be good as well because I could do with some more checks.
Right.
You know, I have like one good example,
Right.
and I maybe have some other checks I would
Yeah.
like to do, but yeah, this is probably a good area for
Yeah.
checks.
I mean, you can also, as you kind of saying, you can check 2D n equals 2, 2 supersymmetric free
Yeah.
theories, which have these huge Nurian moduli spaces as their conformal.
Because
manifolds.
you can tack on the fermions, they don't modify the couple manifold structure.
Okay, yeah,
You just introduce some other operators,
Yeah.
and those
I
operators
understand.
have, protected dimension anyway, so doesn't enter your story. So you can just treat the free bosons. The operator that have, non-trivial dimensions, like looking according to you, unprotected will be the 1D momentum operators.
like same as free boson.
Yeah, yeah.
So what is the sphere partition function?
The sphere function is given by the exponential of the Killer potential. So again, the couple manifold in that case, if you have even number of bosons, the couple manifold is scalar, there's Killer potential.
Ah, so it's just this
In fact, if you have
g log r squared,
Yeah, yeah,
and I just write down Kler potential. and-
yeah, yeah,
How
yeah.
do I know the right Kler potential? Though? 'Cause when I have
Yeah.
supersymmetry,
Yeah,
I feel like there's like
This is a free theory. It's the obvious.
yeah,
Taylor
it's a,
potential.
I mean, yeah,
the one that only depends on.
I think it's the same.
You just-
Like if you have two free bosons, it's
Yeah.
literally the same
Because-
moduli space.
no, but that is
Yeah.
talking about maybe like a couple manifold, I should split them, right? There's the chiral part, there's CC part, there's AC part. Of course, the unambiguous sphere partition function is like they see one part, not both.
Yeah.
But you can make that choice. Yeah, once you fix your compact structure, I mean, yeah, there's a choice you get.
Yeah. Okay, I'm gonna have to get you to
Yeah.
talk to me more about this.
Yeah, but you can, the
today,
example
later.
is as Brandon was saying, just take two compact bosons.
Yep.
You can tack on, you need two compact bosons, you tack on the two fermions. And that's the simplest to come out to theories with a couple manifold.
Okay, great.
More
great.
interesting would be if you looked at Flavia threefolds or something. Or...
Yeah,
Yeah, sounds interesting. Yeah.
yeah, very interesting work.
Thanks. Please, if you have any more questions.
Yeah, we can ask questions after.
Okay, let's do that.
Thank you again.
Thank you.
Thank you very much.